Hi, everyone. Once you know enough about Taylor series and Maclaurin series and the like, you're actually able to solve what's called the Basel problem, which is a famous infinite series, uh, first solved by, well, you would expect it would be solved by some mathematician named Basel, but it was not. It was first solved by Leonhard Euler, a big name, famous Swiss mathematician. And rather than naming it after Euler, name it the Euler problem or something, they named it the Basel problem after Euler's hometown of Basel, Switzerland. Uh, I suppose they were thinking at the time, everything's already named after Euler. He's so prolific. Nobody's going to be able to distinguish between all his great results if we just keep naming everything Euler's theorem or Euler's method or Euler's result. So they named it after his hometown, which I think is kind of cute. But it's a devilishly hard problem. It stood for I think almost a century before anyone was able to tackle it. People probably had suspicions that this sum was equal to pi squared over 6, but nobody was able to prove it. It was very much a big mystery in the mathematical community for nearly a century. And what Euler did was he came along and he took I'm going to call it a roundabout approach to solving the problem. At first glance, it does not seem related at all, but let's see how it works. It shouldn't take too long, and it's pretty beautiful. So what Euler did was he thought about sine x. Okay, told you it seemed totally unrelated. But yeah, he thought about the function sine x, and he thought to himself, I know a couple fun facts about sine x. Depends on if we want to start with, the Taylor series one or some other obscure one. Let's start with the obscure one. What Euler thought to himself was, I know what sine of x looks like. On a graph, the sine function looks something like this, and it keeps repeating. It's some nice periodic thing. That was not great. What is that? Anyway, not going to be perfect. That's what sine of x looks like. And Euler thought to himself, well, I know a power series for sine x, or a Taylor series or a Maclaurin series or whatever you want to call it. I know that sine can be represented as a series, x to the 2n plus 1 over 2n plus 1 factorial, plus that alternating component in front. And I mean, if we write this out, this looks sort of like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. All the odd powers of x over that odd number factorial summed up in an alternating way. And the first big logical leap that Euler made was to think, this looks like what you might call an infinite degree polynomial. Usually when we say degree, we mean the highest power of x is the degree of the polynomial, but it looks like this keeps going and the power keeps getting higher. So it's sort of like an infinite degree polynomial. And we know some fun facts about polynomials. We know that, for example, so let's do a little sidebar over here. So in the sidebar, we'll have an example. What do we know about polynomials? I mean, I could take the polynomial, let's make it kind of simple, 1 minus x squared over 4. And I know that I could factorize this. I know this is actually a difference of squares. And so I could write it as 1 minus x over 2 plus 1 times 1 plus x over 2. And once I do that, I'm actually immediately faced with the roots or the zeros of the function, right? The x over 2 kind of, and well, the negative x over 2 and the positive x over 2 kind of indicate that your roots are positive and negative 2. in the sense that, if you plug it in for x, then one of the terms becomes 0. If you plug in the other one to the other term, that other term becomes 0. So yeah, so they're zeros of the function. We also know that if we were to plot this function, maybe it looks something like this. Some downward sloping parabola where the roots are where you cross the x-axis, -2 and +2. Right, so multiple equivalent ways of thinking about roots of polynomials. You think, okay, they're the places where the function crosses the x-axis. They're, if you factorize your equation, they're sort of hidden in these little linear factors here. And Euler looked at this sort of infinite degree polynomial for sine, and he thought to himself, well, I know what the zeros of the sine function are. They're 0 and pi and 2 pi, and we might as well go negative as well, -pi, -2 pi. All the integer multiples of pi, basically, including 0. And so he thought, why can't I just factorize sine like I'm doing over here with a standard polynomial, right? I break it up and I say, this should be equal to a bunch of linear terms. You'll have like an x minus 0 for this 0 root. You'll have an x minus 1 minus, let's write it like this, 1 minus x over pi. Right? Because if I plug pi in for x, then that term becomes 0. That's effectively saying pi is a root. Certainly is. Right? Sine of pi is 0. And I should also get the paired version of this. At -pi, you would just have to do 1 plus x over pi. And you could keep doing that. You would get a couple for 2 pi that look similar, but just have 2 pi in the denominator. Okay, we're encroaching on sidebar territory, but let's just put ... There are infinitely many zeros of the sine function, so this goes on forever, but perhaps that's a valid thing to do. It turns out it is. You can factorize sine like that into linear factors. It's sort of absurd thinking about it now. But yeah, Euler kind of took that for granted. He thought that's a reasonable thing to do. And it took a little while for someone to prove that that's actually allowed, but sure, it's allowed. So he looked at this sort of infinite product. And the genius that was Euler said to himself, well, first of all, I don't like this term. This term is sort of not like the others. It doesn't come in a pair. So this is just x. Let's divide by x on both sides of this equation. Right, so on the left-hand side, remember we had sine x from here. So we're going to divide by x on both sides. So that should kill this term and just leave the rest, right? Because it's an infinite product. So the rest of the terms remain. And for the rest of the terms, why not group them up together? Right? So group pi with -pi, right? Any pair of roots get grouped together, and I combine them, and this looks like it's like a difference of squares again. So might as well write it as 1 minus, and just foiling it out, you would get x squared over pi squared. For the next two terms, you would get something similar. You'd get 1 minus x squared. And this time you'd get the quantity 2 pi squared. So that's 4 pi squared. The next terms would correspond to the roots of positive and -3 pi. So that would be 3 squared pi squared, so 9 pi squared, ... Okay, so all I've done is I've moved this term over to the left-hand side by dividing by it, and then grouped pairs of nice terms together to land me here. And there's absolutely no reason you would ask this question, but you might think, what does this look like when I multiply it out? actually, maybe there is a reason. Maybe that's a natural thing to ask, right? It's a bunch of like binomials multiplied together. What happens when I multiply them out? And then you have to think, how do I FOIL infinitely many terms together? Well, it's sort of just the distributive process in action. You would get, 1 times 1 times 1 times 1 times 1, blah, blah, blah. And you'd get 1 times, maybe times this term, times 1 times 1 times 1. And then 1 times this term, times 1 times 1 times 1. And, vice versa, you'd get all these terms multiplied together. Essentially, to multiply this out, you just pick one term from each set of parentheses and multiply it with a term from the next set of parentheses. And you have to pick every single combination. But of course, there are infinitely many terms, and it gets infinitely ugly. So Euler said to himself, what if I just concern myself with the x squared term? Right, so I definitely have a constant term. If we multiply all the ones together, we just get 1. Maybe that's unimportant. If we multiply, if we ever end up multiplying 2 of the x squared terms together, we'll get x to the 4th. And then no matter what I choose after that, even if I just choose ones forever and ever after that, it's too late. I've already gone too far. My power is already x to the 4th or something bigger. So that's bigger than I want. That's bigger than x squared. So how do we get the x squared term? Well, it sounds like we'd have to have some nice middle ground between those two extremes. Instead of only picking the constants, or instead of picking multiple x squareds, we should just pick a single x squared and then make sure every other term we pick when we're multiplying is a 1. So, okay, that's a valid choice, x squared over pi squared, then 1, 1, 1, 1, 1. Another valid choice is x squared over 4 pi squared. And then choose the one here and the one here, and then all ones after that. Another valid choice is, I take the first 2 ones, and then I take this x squared term, and I take all ones after that. So each time only select one of those x squared over some multiple of pi, and then select ones for everything else. And in doing so, your x squared term will essentially just be, well, negative x squared over pi squared minus x squared over 4 pi squared minus x squared over 9 pi squared, dot, dot, dot. You've essentially just grabbed each of these terms, right? Because you're multiplying them each by an infinite list of ones. It just spits out one of those for each. So that's at least the x squared term. We could make this look nicer if you want. We could say to ourselves, well, they all have an x squared on them. They're all negative. They all have some multiple of pi squared in the bottom. So, okay, let's bring out the negative. Let's bring out the pi squared. And then let's have some sum here. So this is, 1, 4, 9, etc. So let's write like this: 1, 1/4, 1/9. And let's not forget about the x squared they all had, and we'll just put it on the end to make it look nice. But now, let's focus on this coefficient. So the x squared isn't going to concern us very much, but this coefficient is going to turn out to be useful. Coefficient of x squared is just negative 1 over pi squared. And the rest of it, you can write as a series from n equals 1 to infinity. And sure enough, this is sort of the series I started with, right? These are the reciprocals of the squares of the integers. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, etc. So somehow this weird thought process led Euler back to the series that we were talking about at the beginning. But it still doesn't answer the question of what on earth is this equal to? Right? That's still a big question mark. Sure, it's a nice fun fact that if you take sine x and you divide by x and you factorize it into linear terms and then group them nicely and look at the x squared term that results from this infinite product. I mean, that's such an absurd chain of reasoning, but if you can follow it, then sure, it comes to a nice conclusion that that coefficient looks like this infinite series. But how is that useful? Well, Euler said, let's go back to step one. Let's look at sine x over x in a different way. We know that sine x over x has a Maclaurin series. N equals 0 to infinity. It's alternating, and then you get your x to the 2n plus 1. But notice we're dividing by x, so we lose 1 power on the x, so I'll just leave it as x to the 2n. And then I have 2n plus 1 factorial on the bottom still. And of course, I could write this out as always. The n equals 0 term would give me just 1. The n equals 1 term would be a minus x squared over 3 factorial. Then I'd get x to the 4th over 5 factorial minus x to the 6th over 7 plus dot, dot, dot. And so Euler said, I have 2 facts about sine x over x. I know that the coefficient in front of x squared has to be this. And yet, the coefficient in front of x squared also has to be this. Therefore, these 2 expressions that I've highlighted must be equal. And this is how a lot of discoveries in math are found. You take 2 completely different approaches to a problem. You reach answers that look completely different. But if each of your chains of reasoning were correct, then the end results must be the same, right? And so, in fact, you can just write this down, -1 over pi squared times the series of the reciprocals of the squares has to be equal to -1 over 3 factorial. But I mean, mess around with this a little. They're both negative, so multiply by a negative sign, multiply by pi squared, just trying to isolate this series, just working with it algebraically at this point. And the answer, miraculously, I mean, there's no other way to say it other than it's miraculous. The answer just pops out, right? The negatives cancel. You get a pi squared on top because you multiplied by pi squared. 3 factorial is 3 times 2 times 1, that's 6. Look at that. Beautiful result. Exactly what we wanted up in the beginning to prove that that series, in fact, summed to pi squared over 6. And it only took knowing some Taylor series, looking at a particular coefficient of x squared, and thinking of some absolutely absurd way to turn sine of x into a product of linear factors. That's the interesting thing, in my opinion, that he was able to do that. But there you go. That's how you solve the Basel problem. And don't feel bad. I guess Euler wasn't like Newton. He didn't do this when he was like a kid. I think he was like 28 when he solved this problem. So you still have your chance to make your mark on the mathematical world if you desire to do so. You just have to sit around and contemplate some weird patterns. Think long enough and hard enough and you can get there. Anyway, I hope you like this as much as I did. Thanks for watching.